Welcome to Hartman Math. Before we get to law of cosines, let's review the law of sines, or at least part of it here with our warm-up. Go ahead and pause here as you work through and solve the triangle or triangles. And play when you're ready. Alright, so we are going to need to find the height, and the reason we need to find the height, our given angle, which means opposite is here, opposite is not longer than or the same length as other. So that means that more than likely this is either 0 triangles or 2 triangles. If it's 1 triangle, it would have to be a right triangle, but unlikely. So we find the height, other, times the sine of the given angle, 6.7. So this is long enough to make a triangle, and therefore it makes 2 triangles. So it's a 2 triangle case. Here's our situation, triangle number 1 with angles D, E1, C1, and then if we swing the 7.9 in, here's our second triangle right here with angles D, E2, and C2. And C1 you should have gotten, or at least triangle 1, you should have gotten angle C1 to be about 58.02 degrees. E2 at the top here, 85.98 degrees, and side length E1, 13.41 units. And then our second triangle, again, so if we have this, then we're going to go right here being the supplement, so 121.98 degrees, and that makes the little angle up on top now 22.02 degrees, and the shorter E2 length, 5.04. And this is lesson 6.2, law of cosines, which is going to handle our oblique triangles, solving them in an SAS case and an SSS case. Standard form, a squared is equal to b squared plus c squared minus 2 times b times c times the cosine of a. That's going to be side angle side. So we would be looking for the one missing side first, and that would be a. So we could, if you wanted to, just square root this right away, say a is the square root of all of this. And the way it works out, if we just kind of logically think through it, it's the sum of the 2 squares of the sides that you know, minus 2 times their product, times the cosine of the angle that's included, the one that you know. If we then solve that equation for cosine A, if we're looking at a side, and you want to find angle A, well, the cosine of A is equal to the fraction, the sum of the squares of the sides that create that angle A, minus the square of the opposite side to A, divided by 2 times the product of the sides that are making the angle. So side, side, we want to solve the triangle, find all of the missing sides. Okay? And the way that we want to approach this with the law of cosines is to find the largest angle first. And the reason that we want to find the largest angle first is, as you saw in the formula, the calculations for law of cosine aren't necessarily as easy as law of sines. So once we find one angle, then we might start using law of sines to find others. But the limitation in the law of sines is because if you're doing it to find an angle and you're then pressing inverse sine, the range on that in terms of degrees is negative 90 degrees to positive 90 degrees. It cannot give you an obtuse angle. So if our largest angle is obtuse, law of sines isn't going to be able to find it. That's why we want to go after it first with law of cosines. Because remember, if we do inverse cosine in degrees, the range is 0 degrees to 180 degrees. We have no problem with the obtuse angles. So we're going to go after F. It's opposite of the longest side, therefore it's the largest angle. So as we set this up, we're going to say the cosine of F is equal to, on top, 12 squared plus 19 squared minus 22 squared over 2 times the product of those two. Okay. Careful as we do this. Remember, depending on what your calculator looks like, if you're doing, you might need some parentheses up here and here for order of operations issues. But now we're ready to go inverse cosine, and like we did in the previous lesson, we're going to round to 2 decimal places. 87.36 degrees. So now from there, we could do the process again if we wanted to. That's probably be the most exact, but we could also use law of sines at this point and go after one of the other angles. And that was not obtuse, but it was the largest angle, so it guarantees that the other ones are not. So either one of the other angles, if we go after E, and I kind of always want to go after the smallest just to be safe, but it really wouldn't matter. 12 over the sine of E is equal to 22 over the sine of 87.36 degrees that we just found. Cross multiply. Sine of E would be this fraction, so take the inverse sine of that fraction. And we're going to get about 33.02 degrees. And then 3 angles have to add up to 180, so we get that. So depending on the approach that you take, because if you had gone and maybe done this one first by law of sines, the rounding might just be slightly different. Or if you had continued and done law of cosines again, which is probably going to be a little bit more exact, the rounding might be a little bit different. So if you're using web assign, it's usually built in to accept a little bit of variance there due to those things. All right, checkpoint. Another side, side, side situation. Pause here as you work through. Hit play when you're ready. All right. You might have run into some issues there, I don't know. If we were going after the largest one first, that would be angle A. Not necessarily because of the picture, but because of the 87 being the longest side. So if we do that, it's going to say some sort of a error, a domain error. And the reason is that's not a triangle. You cannot have triangles of sides 87, 35, and 49 because the triangle inequality theorem states that if you add up any two sides, they have to be greater than the third side. 35 plus 49 is not greater than 87. We couldn't actually make a physical triangle with those measurements. That's why you got that error message there, because this ratio is larger than 1, and that is not in the domain of the inverse cosine function. Example number 2, side angle side, side angle side. In that situation, we go after the third side first. And this is by the standard form of the law of cosines. So we would say p squared is equal to 19 squared plus 12 squared minus 2 times their product times the cosine of the 38 degrees, the included angle. And then we can just square root all of that. Can square root it. Usually when I'm operating with a calculator, it's easier just to raise to the half power, which is the same thing as square rooting it. So that's what I did. You get that it's about 12.07. From there we could proceed into law of sines if we wanted to, or cosines, but my preference is sines. Once again, I wouldn't go after Q. It might be obtuse. And law of sines can't find that. So I'm going to go after the small one, R, see if I can do that one. So by law of sines, 12 over the sine of R is going to approximately equal to, because since we've already rounded, 12.07 divided by the sine of 38 degrees. Again, we cross multiply. Sine of R is going to be 12 sine 38 degrees divided by 12.07. Inverse sine on both sides. We're going to get about 37.74 degrees. And then we can find Q from there, since they all three have to add up to 180 degrees. You get about 104.26 degrees for that one. So in a side angle side, we want to go after the one missing side first, and then go after angles. Checkpoint. Go ahead and pause here, as you can see if you can work through this bearings problem. Ship leaving port, heading straight north 15 miles, then changes course north 32 degrees east, travels for another 80 miles. How far is the ship from port? Again, pause here, hit play when you're ready. right, as long as we can get the bearing, the problem is actually itself fairly easy. So here's our sketch. We're going to go north for a little bit. And then from there, from the north line, well, let's draw the north line 32 degrees towards the east. We're going to connect there. And this is 15 and that's 80. We just need to figure out this angle, which is not difficult. Because if that's 32, this is a linear pair and therefore supplementary. That makes that 148. And there we go. Our distance. Distance squared is equal to the sum of the squares of those two sides minus 2 times their product times the cosine of the included angle. You get about 93 miles or 93.1 miles, depending on how extreme we want to round. Definitely don't want to go any more than that. All right, example number 3, little star there. So this is a softball setup, a softball field, a softball infield with mound and so forth. The mound, and they're really talking about the center of the mound being 43 feet from home plate, and the distance between bases being 60 feet. Question is, how far is the mound from first base? The common misconception, by whether it's looking at the picture or whatever, is thinking that this is an isosceles right triangle, and that this is 45 and this is 45, and that's the incorrect assumption. That is not necessarily the case, and it's not the case. But that's okay, because we have all the information that we need. We know that this distance is 43. We know that this distance is 60. So it's a fairly easy law of cosines problem, where we have side, angle, side. Because since this angle, we're talking about a square here, and this is 90 degrees, it is split equally as being right 45 degrees. So side, angle, side, we're ready to go. 43 squared plus 60 squared minus 2 times their product times the cosine of 45 degrees. That would be h squared, or we can proceed directly to h equals the square root there. Type that in. You get about 42.4 feet. Checkpoint, another bearing problem. Pause here, get the sketch, work it out, find the distance and bearing from point C to point A. All right, here's our sketch. Plane flies 720 miles from A to B with a bearing of north, 65 degrees, so 65 takes us to there, 65 degrees, 720. Then we change course north and 28 degrees towards the west, so still kind of continuing the same direction and traveling 528 miles there. Now, some of the important things for us to be able to find out as we create our triangle is this angle here. So since this is 65 degrees, and we've got a north line here and a north line here, and a transversal, same side interior angles are supplementary. So 180 minus 65 gives us the 115, which is right here. We also need this angle. We already knew that was 28 degrees. So if we add those two together, we're getting the 143 degrees. And we knew both of those, so we could find the distance. So that was one of the things we were looking for, is the distance. So pretty straightforward law of cosines, find the distance. And it's about 1,185. Since it's such a long distance, rounding it beyond the nearest mile doesn't really make a whole lot of sense. From there, we can find angle C. Now when we're talking about angle C, we're talking about in the triangle, so this one right here. So law of sines can find that. Our D here, 1,185 divided by the sine of the opposite angle, the one that was created by adding those two angles, 143, is equal to the 720 over the sine of C. And that's going to tell us that C is about 21.45, but that's not a bearing angle because it's not touching a north or south line. We need to take it all the way to here. So we found this one. We need to add this one. And we do know that one, again, some basic geometry. North line, south line, they have to be parallel. Transversal, these are alternate interior angles, and they have to be congruent, so same measure. That's 28, that's 28. So if we add 28 to our 21.45, we're going to get our bearing angle. From south, we're going to swing it 49.45 degrees towards the east. Heron's area formula is another way to find the area of a triangle in a side-side-side case, so knowing no angles, not knowing like the height of the triangle, just knowing the three sides. Heron was a Greek mathematician in the early AD years. And it involves finding S, the semi-perimeter. So it's half of the perimeter. So add up the three sides, divide by 2, you've got the semi-perimeter. Then the area is the square root of the product of the semi-perimeter times the semi-perimeter minus each of the sides individually. So 4 things being multiplied here. Example number 5, we've got a triangle, find the area. We're going to start by finding the semi-perimeter, adding up the 3 sides, and dividing by 2. You get 43. So the area is going to be the square root of 43 times 43 minus 30, times 43 minus 23, times 43 minus 33. Calculate all that out. It's going to be about 334.37. Since this is just kind of an abstract problem here, we are rounding to 2 decimal places. So it would be like a word problem, or that might be something else. That's it for today. See you next time.